Assalamu alaikum, my dear students. Welcome to the final video of our vector spaces series. You have done a great job following along. Today we are going to solve exercise 8, which is a fantastic summary of everything we learned. We will extract bases, find dimension, and finally discover what it means for two subspaces to be supplementary. Let's dive right in. We are given two subspaces in R3. Let's start with W1. To find a basis, we need to extract the vectors hidden inside this equation. We have one equation and three variables. Let's isolate x and write this. Now we write a general vector in W1 using this substitution. And we replace x by minus y minus z and y and z. Next, we separate the variables y and z, and we can write y multiplied by the vector minus 1, 1, 0 plus z times the vector minus 1, 0, 1. These two vectors span W1. Since they are clearly not multiples of each other, they are linearly independent. So the basis of W1 is this family of vectors. I have a remark. We can quickly verify that these vectors are correct by calculating the scalar product with the numeral vector to the plane W1, which is n equals to 1, 1, 1, which is the coefficient of x, y, and z. And to calculate the dot product, for example, I name this V1 and this second vector V2. To calculate the scalar product or the dot product, I write first this, then we multiply each component with its neighborhood, which is 1 times minus 1 plus 1 times 1 plus 1 times 0, which is clearly 0. Then n is orthogonal to V1, and we can may calculate the same thing with the vector V2. And here we have minus 1 plus 0 plus 1, which is also 0. Then n is orthogonal to V2. To visualize this, we have our plane W1 that contain the origin O, and here our two linearly independent vectors V1 and V2, and the normal vector must be orthogonal because there are exactly two vectors in this basis. The dimension of W1 equals 2, which is the number of vectors in the basis. Let's apply the same thing with W2. We take a general vector x, y, and z. Since x equals to y, we can write this. Then we separate the variables and we write. So the vectors 1, 1, 0 and 0, 0, 1 are linearly independent and span W2. They form a basis for W2. And the dimension of W2 is also equals to 2. In question 3, we have to show that W1 plus W2 equals to R3. What is the sum of two subspaces? It is simply the space generated by the union of their bases. We have 4 vectors in total from our two bases, but we are in R3. I am going to take these two vectors, okay, and one vector from the second basis. So let's pick 3 vectors for our union. For example, minus 1, 1, 0, and minus 1, 0, 1, and 0, 0, 1. To prove this forms the whole space R3, we just need to show they are linearly independent and span R3. To show they span R3, we can demonstrate that any general vector x, y, and z can be written as a linear combination of these 3 vectors. To prove it, I am going to first write this. And we have to find A, B, and C. So we obtain 3 equations. The first one, minus A, minus B. The second one is A, and the last one is B plus C. Okay. From the second equation, we have y equals to A. I am going to plug this here, and we can write B equals to minus y minus x. Then we substitute this here, and we obtain C equals to z plus y plus x. To verify that it is correct, I am going to write this B is minus y minus x, and C is z plus y plus x. By calculating this, we get minus y and plus y plus x. Where is the third vector? I forget to write the last vector. Okay. The second component is y. The third component is minus y minus x and z plus y plus x. We simplify. Here we have our x, we have our y, and we have our z. We proved that our vectors span the entire R3. Now, to prove that these vectors are linearly independent, I am going to use another method. We are going to calculate the determinant of the following matrix. Minus 1, 1, 0, minus 1, 0, 1, and the third vector is 0, 0, 1. Now, I know we haven't officially learned what a matrix is yet, but to simplify, think of it as just a table of numbers. I am going to show you how to calculate its determinant step by step. We consider this as a little sneak peek into chapter 3 of our second semester. So to calculate the determinant, we choose first this element and we eliminate the first row and the first column. Then we have minus 1 times the determinant of the rest, which is this. Now I am going to put a minus 1 here. Then I take my second element, minus 1, and we multiply it by the determinant of the rest. Here we eliminate the second row and the first line, and we have 1, 0, 0, 1. The third number to calculate is the third element of the first row. We eliminate this row and this line, and we calculate the determinant of this 2 by 2 matrix. So we continue. Here we have minus 1. To calculate the determinant of a 2 by 2 matrix, we do this. 0 times 1 minus 1 times 0. Here I have plus 1 times the determinant of this matrix plus 0 times a number which is 0. Here I have 0. Here I have 1. Then the determinant of A is equal to 1. Then our vectors v1, v2, and v3 are linearly independent, and this family is free. Because they span the space and are independent, adding W1 and W2 together covers the entire 3D space. Finally, question 4. Are W1 and W2 supplementary? For two subspaces to be supplementary, two conditions must be met. The first one is W1 plus W2 equals to R3. We just proved this in the previous question. And the second condition is that the intersection of W1 and W2 equals to the 0 vector. Let's calculate the intersection. A vector belongs to W1 enter W2 if satisfied. First I need to return to W1 and W2. Okay, I'm going to take this. Okay, copy. A vector belongs to W1 enter W2 if it satisfies both equations at the same time, which is this equation and this equation. Let's substitute y with x in the first equation. We obtain 2y plus z equals to 0. Then z equals to minus 2y. So any vector in the intersection looks like this. X equals t, y equals to t, and z equals minus 2t, where t is a real number, which is a parametric equations of a line. Let me draw this to visualize the intersection of two planes. Okay, we have our W1, and the second plane is like this, which is W2. The origin must be in the two planes, and here we have the intersection, which is a line that passes through the origin and is included in W1 and W2. 2D planes in 3D space will always intersect in a line, so they can never be supplementary. Because the intersection contains a whole line of vectors and not just the zero vector, the second condition fails. Therefore, the W1 and W2 are not supplementary. And that's it. We verified the bases, combined the spaces, and visually checked their intersection. This brings our video series on vector spaces to close. I highly encourage you to rewatch these videos as you prepare for your exams and make sure to practice these exercises on your own. Thank you all for your hard work and attention. Good luck with your studies and bye.